Hi everybody, welcome to another video in Business Calculus, section 11.1. First, derivatives and graphs. So first, we define increasing and decreasing. The function is increasing if the value is increasing when x is increasing. The function is decreasing if the value is decreasing when x increasing. So here we have like x1 and x2. If the value is increasing as x increasing, then it is increasing. If the values for x1, x2, if the values x increasing and the values of y decreasing, then it is decreasing. Obviously, if the graph go like this, that is increasing, and going down, that is decreasing. So that is obvious. Now, but how is that related to what we learned in the previous section, namely derivative? And conveniently, we have defined derivative as the slope of the tangent line. So if we draw a tangent line for both of those cases, as we see, if the function is increasing, the slope of the tangent line, the tangent line goes up. If the function is decreasing, the tangent line goes down, and consequently, when the line goes up, the slope is positive, therefore derivative is positive, and when the line goes down, the slope is negative, or the derivative is negative. So we tie increasing and decreasing to the derivative of positive and negative. Of course, that have to be for every point in the interval a and b. Right. Next, we define critical values. Critical values x in the values of x in the domain where derivative equal to 0 or derivative does not exist are called the critical values of f. All the books use critical number. And all the books use critical points, but I will reserve the critical points. When we talk about points, we refer to a point would have x and y coordinates. So we will not use the critical points to refer the values of x. We use critical numbers to refer the values of x, and we call the critical values is values of just the x values, or just the x values. We can say critical values or critical numbers. Right. Now, even though when we look at this definition, it looks like there's only two parts, where derivative equal to 0 or where the derivative does not exist. But don't forget that it has to be in the domain. So this is also important. If it is not in the domain, the function is undefined at that point. So the point is not on the graph. So it cannot be increasing or decreasing, cannot be anything. So even though in the this definition look like there's only two, but actually the in the domain part is very important. All right. Now, also we in this class once again, critical values is where we have all three of this. Critical numbers where we have all three of this, we refer that to the x values that have all three of these properties. Critical points, again, anytime we talk about points, we refer the x and y coordinates. So this is not the point. However, to make things easy, we refer this particular, if we only have these two conditions, 1 and 2, where that is in the domain or not, it doesn't matter. If we have those two properties, we call that a partition number, which will have some use later. So partition numbers, if they have these two properties. Right, I'll just go straight to it. Find the critical values for the function. Well, easy, based on definition. First we'll take derivative. That gives us 8 minus 2x, and we will consider these two cases. The first is where derivative equal to 0, and the second case is where the derivative does not exist, right? So when 8 minus 2x equal to 0, we can solve for x minus 8 on both sides and divide by negative 2. So if x equal to 4, right, we have 1 point. And when derivative does not exist, notice that what we have here is polynomial, so that is defined everywhere. So we say f prime d is defined everywhere. So in that case, simply we just write when x derivative equal to 0, we have x equal to 4. Derivative does not exist, we have nothing. We just write none. Right. Now, remember, critical values, we need three things. Derivative equal to 0, derivative does not exist, and they have to be in the domain. So we just simply check what happened at x equal to 4, substitute into the original function. The function at 4. We do not need to know what is the values at x equal to 4. All we need to know is the function is defined or not, and this is equal to 16, well-defined number. So this is defined. I'll just say it's defined, meaning in the domain. The first problem I write a lot of details. So for the first one we have that. I mean, notice that this is either or. So we have maybe we have this, we have that. So it might not be both. So we have x equal to 4. It is in the domain. So the critical values it's just 1, 4, right? So derivative equal to 0 does not exist. Make sure it is in the domain if we want to find the critical values. Now, next we determine where the function is increasing and where the function is decreasing. Increasing is where derivative is positive, and decreasing is where derivative is negative. For that, we will construct a sign chart. A sign chart is something like we did on the one of the section before. We just make a sign chart for the derivative. So the top is just like the number line. I wrote a number line on this side, negative infinity to infinity, and the critical values, or in this case we only need partition number. I will distinguish that in a moment. So we have 4, right? And the derivative we have is 8 minus 2x. And when that happened, derivative when x equal to 4, derivative is equal to 0. So that's what we have, right? Just that called the sign chart. Right, next, to determine the signs in the sign chart, I just pick a value, substitute in here. I will choose less than 4 and greater than infinity. Why don't choose 0? I'll choose 5 here. And then we put in the derivative here, because the sign chart for the derivative. When x equal to 0, 8 minus 2 times 0, so it's 8. When x equal to 5, 8 minus 2 times 5 is minus 2. So for 0 is positive, and for 5 is negative. We just need to test one point. And then if it is positive, derivative is positive, the function is increasing. If not, it is decreasing. So we will write the function is increasing on the interval of negative infinity to 4, and decreasing on 4 to infinity. Very straightforward. And just like I mentioned before, when we do the inequality for the rational function, there are 4 possibilities for numbers. It's undefined, equal to 0. So when we take care of the case when it equal to 0 does not exist, we only have 2 things left, positive or negative. And positive give us increasing and negative give us decreasing. Very straightforward. Right, next. We have more example here. Find the critical values of the function in the interval where the function is increasing, where the function is decreasing. Right. So first, of course, find derivative, and after that, find critical values, and then the sign chart. So look like the problem may be long, so try to write small. Right, so first we find derivative, and then we find the critical values, right? So this is the function. To find the derivative, we will use the chain rule, 1 minus x to the 1/3, all right? So something to the 1/3 power, this is not what inside the parentheses. Derivative of that is 1/3, the parentheses, the power, original power minus 1. 1/3 minus 1 is minus 2/3. And then derivative of the parentheses. Right? So that is derivative for the chain rule. Doesn't matter what inside the parentheses. Now, we have 1/3, 1 minus x to the negative 2/3. Derivative of 1 minus x is negative 1. Negative and negative. So that gives us negative 1/3, 1 minus x to negative 2/3. Right? Negative exponent we can move to the bottom. Original power turn to positive. Alright. We really need that. Right, what's next? Is to find critical values. Critical values is where derivative equal to 0 or derivative does not exist. Here we have a fraction or rational function. It is equal to 0 if the top is 0 and does not exist, meaning the bottom equal to 0. On this one, the top is just negative 1 and that's not equal to 0. So we do not have anything here. So just like last time, we write none if there's nothing there. Right, bottom equal to 0. Divide by 3 on both sides. Right, anything raised to some power equal to 0. The only case for that to happen is when the inside is equal to 0, right? Anything raised to anything that equal to 0, the only case that equal to 0 is the base equal to 0. So 1 minus x is 0, so x equal to 1. Now we have 1 values. Right, so again, if we have not checked with the domain, then what we have here is a partition number. Right? Partition number doesn't have to be in the domain, so we haven't checked it. So this is a partition number. Now, if we want to, we'll check. Actually, in this case, we need to find critical value, so we do need to check. So when at x equal to 1, the function, remember, we check for the domain, so we use the original function. I'll write that. F of 1 equal to 1 minus 1 to the 1/3, and that is 0, which is 0, and it is defined. So x equal to 1 is a critical value. Right. So we check with the original function because we need to know, we need the point to be in the domain. Right, so that's the first part. The second part is where we use the sign chart to test where it is increasing or decreasing. Alright, so we have the number line on the top. And only one critical values have 1. And we have the derivative -1, 3, 1 minus x to the 2/3. Right. Now notice when x equal to 1, it is undefined, or derivative we usually say does not exist. As opposed to the last problem, we have equal to 0, so label that clearly on the sign chart. Right, and then we'll pick a point between -infinity to 1, that will be 0, and between 1 and infinity, that will be 2. Right, that's simple enough. You can just use the calculator. For example, if we say 0 turned to x, and we just have -1, or just type this as the derivative, -1 times 1 minus x to the -2/3. And then divide by 3. Right, we have negative there. And then we'll take 2 store into x. And do this again. And we should also have negative. So it's decreasing and then decreasing. And just in, if you're curious, we can always graph it. See the function going down and then down. Alright, so notice that it is decreasing from -infinity to 1 and then from 1 to infinity. It's not increasing all the way from -infinity to infinity. So we have to write 2 separate intervals. Increasing -infinity to 1 and then 1 to infinity. Right, so that's what we have. Right, so take derivative equal to 0 does not exist, and if we want the critical values, check with the domain. Check with the original function. Now if we just want the increasing or decreasing, if we want the interval, we don't really need to know if it is in the domain or not. So the sign chart, we use partition number, not the critical values. Right. Next we have this function, so we will do the same thing. We take derivative, and of course that we can suddenly we can write this as 1 over x minus 2 as x minus 2 to negative 1, and we can use the chain rule, so just like the previous one. On this one I've used the quotient rule. U equal to 1, v equal to x minus 2, and u prime equal to 0, and v prime equal to 1. Right. This is an advantage of using the quotient rule. I will tell you when we get there. So here we just take derivative of a quotient rule, just a quotient. Right. U prime v minus u v prime over v square alright, so 0 times anything is 0. You just have negative 1 over x minus 2 square. Right. Now the reason I prefer to use the quotient rule here is because we prefer to have a quotient, a big fraction like this. When we have a fraction like this and we find critical values, we set derivative equal to 0. That is the top equal to 0. Derivative does not exist, the bottom equal to 0. So it is to our advantage to have, if we can write as one big fraction, we do that. If we do this, eventually we will have to move it to the bottom and to get to the fraction anyway. So since we expect to have a fraction, why don't we just use the quotient rule? And of course you can use anything, but it is to our advantage to have the big fraction like this. It's easy to work with. Now we find the critical values. It is where the derivative equal to 0. That's where the top is 0. Derivative does not exist, meaning the bottom is 0. But the top is just negative 1 and we don't have anything, so that's none. And the bottom is x minus 2 square equal to 0. Once again, anything equal to 0, anything raised to any power is equal to 0. The base must be equal to 0. So we have x equal to 2. Right. So we have the partition number x equal to 2. Just need to check with the domain, meaning put it in the original function. At x equal to 2, evaluate at the original function because the domain is of the original function. Put 2 in for x. Sorry. That's what we have. And we have 1 divided by 0, which is undefined. Right. So what that means is we have a point which is a partition number, but it fails because it's not in the domain. So it is a partition number, but not a critical number. Right. So we say no critical values because that point makes the function undefined. So it's not in the domain. No critical point. But we do have the partition number x equal to 2. And we use the partition number to put on the sign chart. Hence the term partition number. Right. So we have x equal to 2 as the partition number. Right. And then we go to the second part where we construct the sign chart. Where we determine the function is increasing, decreasing. Right. So we have derivative is that. And on the top we have a number line. And the partition number 2. That number make the derivative does not exist because that comes from the does not exist column. Right, partition number, so that divide the table. Right, test point, pick a number between negative infinity to 2. I always choose 0 when that's an option. And then 2 to infinity to 3. And then substitute into the derivative. Right. So we have 0 is down to x. And derivative negative 1 divided by x minus 2 square. So that is negative. And then we put 3 in for x. And that is also negative. So if that is the case, we can say, by the way, we might want to put a function here. So the function derivative is negative, the function is decreasing, and then decreasing. So the answer pretty much like the previous problem. So it is increasing. Sorry, I'm glad we caught that. So on the previous problem, we say increasing or decreasing, and this is decreasing. And on increasing, it would be none. Right. So yeah, sorry about that because clearly it's going down. So it's decreasing. Right. So this problem, increasing. There's no interval where the function is increasing and decreasing. Negative infinity to 2 and from 2 to infinity, not going all the way from negative infinity to infinity. Right. By the way, if we only ask where the function is increasing or decreasing, we don't need to find critical values because we only need partition numbers so we can divide the table. If we only want the interval. Right. So that is that. Right. One more problem. This. So f of x equal to that. Once again, check derivative equal to 0 does not exist, and then check with the domain for the critical values. The sign chart will give us increasing or decreasing. Right. So first, we check derivative so we can make it equal to 0 does not exist. Derivative of 8 ln of x. Derivative of ln of x is 1 over x. Derivative of x squared is 2x. Right, so that gives us 8 over x minus 2x. Just like last problem, we do prefer to have one big fraction. So let that write that over 1. And then we multiply x on the top and x on the bottom. So we have x at the bottom. So that gives us a over x minus 2x squared over x, common denominator x, and then a minus 2x squared. Right. We have one big fraction, so we can say it equal to 0 does not exist. Right, there's one thing we need to worry about. I will tell you when we get there. So, but it's Greek values. Right, so derivative equal to 0 does not exist. That's where the top is 0. Derivative does not exist. That's where the bottom equal to 0. One important thing we need to watch out for. The top is a minus 2x squared equal to 0. So we solve for that and solve for 2x squared. Subtract 8. Divide by negative 2. And then take the square root. So that's plus or minus 2. Right. The bottom equal to 0. Bottom is x equal to 0. So we have x equal to 0. So we have x equal to 0, x equal to 2, or x equal to negative 2. However, this problem is different than any other problem. Now let's just, if we have to sketch the graph, a times ln of x. Just clear everything. A times ln of x minus x squared. Of course, here we see where it's increasing or decreasing. That's easy. Just one important thing though. Notice that there's nothing on the left side of the y-axis. Simply because if we check with the domain, ln of x is only defined when x is positive. If we go to the table, you see, if it's negative, it's error. The function is undefined. So for this very big thing, if we want the Greek values, we have to check with the domain. And in this case, the domain of ln of x is positive number. Because if we put a negative number as an argument of the natural log, it will be undefined. So in that case, we only check the positive values. So in this case, the only Greek values is 2. Because x equal to 0 is not in the domain, and x equal to negative 2 is not in the domain. So it cannot be the Greek values. And also, because in the question asks for the function where it's increasing or decreasing, we only focus on the domain. So the sign chart here is slightly different than the sign chart we have earlier. So 2, where the function is increasing or decreasing. So there's a sign chart. I did mention that slightly different than the sign chart that we have previously, because the domain in this case is not all real numbers like previous example. Previous example, the function defined everywhere, so we can write from negative infinity to infinity. On this one, it's not. It's only defined for 0, so we do not write that. We say we will go from 0 to infinity only. Right, the derivative is that. Right, notice that from 0 to infinity there's only one Greek value of 2. And that Greek values make the derivative equal to 0. So we need to label that clearly. Right, that we have a sign chart. And so between 0 and 2, cannot choose 0, so it should be 1, and 2 to infinity to 3. Right? Then put those numbers into the derivative. 1 is turned to x. 8 minus 2x squared divided by x. That will be 6 is positive. And 3 is turned to x. And that is the derivative is negative. So we have the function positive is increasing, negative is decreasing. Right, so the function is increasing from 0 to 2 and decreasing from 2 to infinity. Right, so once again, be mindful with the domain, particular when what we need to watch out for the domain. I'm just going to write the 3 things. Under denominator have to be not equal to 0. Divide by 0 is undefined. Second, under an even root, just say even root, anything inside have to be greater than or equal to 0. Otherwise, even root, a negative number is imaginary, and inside of any log of any base, the argument must be positive. So those are the 3 things we need to watch out for as far as domain goes for a function. Right, so watch out for those cases. Right, so that first part of the function determine whether the function is increasing or decreasing. Next, also from derivative, we can find the local extrema, meaning local maximum or local minimum. Right, first the definition. We call the function values as a local maximum if there exists an interval containing c such that it is bigger than everything else, and local minimum is smaller than everything else. So that's obvious. Now the key word here is local. So what do that mean? What does that mean? So we have a function could go like this. If we talk about the absolute values, the absolute maximum, it would be here, the highest values, and the lowest point is here. But if we talk about local maximum or local minimum, it is locally, we only compare to the points around it. And we compare the points around it, and that is the highest point, so that's the maximum. And we compare the points around it. This is the lowest point, that's the minimum. We do not compare this point to that point because locally we only choose a very small interval to compare the point, not the whole interval. That's why we call it local max or local mean. All the books refer to as relative maximum and relative minimum. It also means the same thing, relatively to points around it. There's maximum or minimum. Right, so we define the local maximum and local minimum. So how does that have to do with derivative? Well, existence of local extrema. If the function is continuous on an interval and c is the number in the interval and it is local extremum, then the derivative equal to 0 or does not exist. Well, that sounds familiar, right? Continuous meaning it is defined so in the domain equal to 0 or does not exist. So that's pretty much the critical values, right? So the critical values potentially may be a maximum or the minimum, but the maximum or the minimum may not be the critical values. So critical values may be local max or local min. I'm sorry, I should write that down because that's important. Okay, if it is continuous, local max, local min, or say local extremum, it have to be continuous. A local extremum guaranteed to be happen at critical values. Critical values may or may not. So we will not have the implication to the local extremum. We will see that in some of our sample. But the way we do this is like finding critical values. Now, first derivative test. Right, in terms of local max and local mean, we define in terms of derivative is like this. Well, that's rather confusing. But if we look on the sign chart, if it goes like this on the sign chart, then that would be a max, a local max. If the sign chart goes down and then up, that is the local mean. That's rather obvious from the sign chart. So pretty much we will do the sign chart and it will tell us where it is the maximum or the minimum. Right, next, find critical values of the function and then find the local maximum and local minimum. Right, just one subtle thing here though. When we talk about local maximum and local minimum, we refer to the y values. So we say that the local maximum, it is the y values of the function that's bigger than the neighborhood of the points. Right. Now we have, that is the function. Now find the critical values and then determine where the local max and local min is at. Right. So first of course, we take derivative. Right, that gives us 3x squared minus 12x plus 9. And then we'll find critical value, so derivative equal to 0 does not exist. Here we don't have the fraction, so we just have just that. And derivative does not exist. Equal to 0. I can divide everything by 3. That gives us x squared minus 4x plus 3 equal to 0. And we solve for x. Negative 4 plus or minus negative 4 squared minus 4 AC over 2a. Of course, you can use any method to solve the quadratic equation. I just use quadratic formula here. That 4 plus or minus square root of negative 4 squared, that's 16, minus 12, so square root of 4, that's 2 over 2. So 4 plus 2 divided by 2, 4 plus 2 is 6 divided by 2 is 3. 4 minus 2 is 2 divided by 2 is 1, so we have 1 and 3. Of course, we can also factor x minus 1 and x minus 3 and we get the same thing. This is a polynomial function, so as far as it goes, we don't have any of this form. So this is defined everywhere. It is defined everywhere, so we do not have anything that make it does not exist. Right, so that gives us the partition number of 1 and 3. Now to find critical values, we do need to check the values. At x equal to 1, just go ahead and find the values because that will come in handy later for this problem. I just simply store 1 into x. And remember, we check for the domain, which is the original function. So use the original function, x cubed, or x times x times x, minus 6x squared plus 9x plus 1. It's 5, which is defined, by the way. When x equal to 3, put 3 in for x. So 3 is turned to x. Again, the original function. So just go up there, evaluate, and if we do that, that gives us 1. Right? So both of them are defined. So we have the critical values. X equal to 1 and x equal to 3. These values, not these values. Right, just say that these values are defined. Right, for local max and local mean, we use the first derivative test, which is similar to doing the sign chart. The sign chart will almost the same, but just one part that is different. Right, number line, because the first domain is all real numbers. Two critical values, 1 and 3. If we just want the sign chart, we only need partition number, but on this one we do need critical values. You see it when we get there. Derivative is equal to 3x squared minus 12x plus 9, and this is a function. Right. When x equal to 1, derivative equal to 0. When x equal to 3, derivative equal to 0. Right. So and then the test point 0, 2, and 4. The test point using the derivative. The domain we use the original function. For the sign chart here is for the derivative. Right. So there's 3-point way. There's another way to find the values. Of course, we can just enter this is the derivative, and then just instead of graph, go to table. Okay, 0 is positive, 2 is negative, and 4 is positive. We only need to know if it's positive or negative. Now, if it's positive, the function is increasing, negative it is decreasing, and then increasing again. Now, based on the graph, this have to be the local max. And this have to be the local mean. And furthermore, we do have the values. When it go up, the maximum values is going to be 5. So we said the conclusion here is the local max is equal to at x equal to 1, and the local mean equal to at x equal to 3. And we go back and check when x equal to 1 the function is equal to 5, and when x equal to 3 the function is equal to 1. So that gives us the local max and local mean. So normally we check this for the critical values. We check this to find the values potentially will be the maximum or minimum. By the way, I said potentially because if we have a sign chart like this, sorry, not that. If we have a sign chart like this, we will not have the maximum or minimum because just going down and then going down. So we may or may not have the maximum or the minimum. But if we do, those points will be at the critical values. Right. Next example here. Given that find critical values, right? Derivative equal to 0. I mean, so for derivative first. Take down the 3, we have 6x squared plus 6x plus 120. Right, 6x squared plus 6x plus 120. Right, derivative equal to 0. Derivative does not exist. So we have that equal to 0. Again, there's no fraction, so we just have that. And plus does not exist, come later. Right, here all of them divisible by 6, so we do that. We have x squared divided by 6, that divided by 6, and divide by 6. Of course, if here we can factor, we do that, but I just use quadratic formula. Negative b plus or minus b squared minus 4 a and c. Of course, did I forgot something? The negative, right? B squared, I mean negative b squared minus 4ac over 2a, right? So give us negative 1 plus or minus 1 squared is 1, and that negative 4 times negative 1 is 4 times 20, 80, and 1, 81. Square root of 81 is 9 over negative 2. So we have negative 1 plus 9 divided by negative 2. That is 9 minus 1 is 8, divided by negative 2 is negative 4. And then negative 1, negative minus 9 divided by negative 2. That gives us negative 10 divided by negative 2, that's positive 5. Actually, we should just go ahead and divide by negative 6. That would be better. But regardless, it works. We have negative 4 and 5. Right? And then when we have the derivative does not exist. And once again, this is continuous everywhere. So we do not have anything here. Right. And then we find the values to check for the critical values at x equal to negative 4 and at x equal to 5. Remember, this is the original function. Right, so yeah, of course, if we want to evaluate, we can always use this. Just make sure what it is that we're using. Negative 2x cubed plus 3x squared plus 120x. Remember the original function. When we check for the domain, right, go to the table, go to negative 4, negative 304. And then go to 5. It's 425. Of course, we can also use, we enter the function negative 2x cubed plus 3x squared plus 120x, and then hit second values and we enter -4. And then 5. Right, we have that. Right. Next, for the local max and local mean, we need the sign chart. Right, -4, -5. Oh, by the way, since this is defined, we have the critical values. X equal to -4, x equal to 5. The sign chart is for the derivative. And those values come from where the derivative equal to 0. Test point 0 would be here, 6, and -5. Right. -6x squared plus 6x plus 120. Remember, we can always use the table, but make sure the what function or derivative that we enter here. So that is the derivative, and that's what we want. We test those points. Second graph. Right. -5, it is -60. Remember, this is sign chart. We only need the sign. 0 is positive 120. And 6 is negative. So decreasing, increasing, and decreasing. So there will be a local max here and the local mean here. So there's a local max. So we write the conclusion. Local max equal to something when x equal to 5, and local mean equal to something when x equal to -4. And we do have the values. When x equal to 5, the original function is 425. And when x equal to -4, it is -304. Right. Of course, when we see the sign chart, the local max and local mean should be obvious. But then, of course, we make sure we do have the values of the function, so it will be defined. Right. Next, we have this function. Find the critical values for that, and of course, determine whether the function increasing or decreasing, and after that, local max and local mean. So pretty typical problem. So first, I will take the derivative of this function. Right. So now I will take the derivative of this, and we'll rewrite this as 4 over x to negative 1, right? Then so we can check derivative easier. Derivative of x is 1. Derivative of that is negative 4 x to negative 2, right? That gives us 4 over x squared. Multiply x squared on the top, x squared at the bottom. And that will be x squared minus 4 over x squared. Right, so that is the derivative. Alternatively, we can write this just, actually this is what I would refer to. Write this as the one big fraction first. So that gives us x squared over x plus 4 over x. So x squared plus 4 over x. Now we rewrite the function as this. Then we use the quotient rule to find derivative. You can just write the function like that and then use the quotient rule to take the derivative. We should get the same thing. Bottom line is when we have negative exponent, rational exponent, try to make that into one big fraction if it's possible. So if it is one big fraction, so we find the Greek values, we say derivative equal to 0. That's where if we have the top is 0, that will be easy. Or derivative does not exist. That's where the bottom equal to 0. Right. Now, the top equal to 0. X squared minus 4 equal to 0. So that gives us x squared plus 4 on both sides equal to 4. Take the square root. Don't forget there's a plus or minus when you do that. So plus or minus 2. Bottom equal to 0. X squared equal to 0. So x equal to 0. That's not that bad. We do need to check though. At x equal to negative 2. The function at negative 2 put negative 2 into x. Negative 2 minus 2 is minus 4. As x equal to 2, put 2 into it. We have 2 plus 4 over 2. And that gives us 2 plus 2 is positive 4. And at x equal to 0, f of 0, 0 plus 4 over 0. This one undefined. So if we want Greek values, there are only two of them, negative 4 and 4. Greek values, we have x equal to, 2 and negative 2. So that is the Greek values. Not that. However, in the sign chart, we will put 0 in too, because for the partition number, the number that divide the sign chart, we do not require the point have to be in the domain, as long as it divides the number line. Right, we will make a sign chart here. We have x. whole number line. Partition numbers, we only worry about this for partition number, so the plus or minus 2 and 0. We need to have 0 because that divide the number line. The sign will change when we go across it. Right. The derivative x squared minus 4 over x squared. Right, when x equal to 2, when x equal to negative 2, the derivative equal to 0. When x equal to 2, the derivative equal to 0. X equal to 0, the derivative does not exist. Just as we discussed in the system. We talk about this in rational inequalities. There's 4 possibilities. Equal to 0 does not exist, positive or negative. We have to find where it is equal to 0 and does not exist first. After that, it can only be positive or negative. And the 0 is a partition number, so it does divide the number line. Alright, now the sign chart. Negative 3, negative 1, 1, and 3. Right. So, have those points and just put in the derivative. Like I said, if we use the calculator, make sure we know what we enter for. So x squared minus 4 divided by x squared. I recommend just put 1 parenthesis for the top and 1 for the bottom, like that. Right, now we can go to the table and look for the values. Right, negative 3, it is positive. Negative 1 is negative. Positive 1 is negative, and 3 is positive. So increasing, decreasing, decreasing, and increasing. So of course there's nothing here. Even though if there is anything here, it's still undefined. So it cannot be anything at 0. And the sign chart doesn't give us decreasing like that. So it's no max or min there either. So we have the minimum and then the maximum. Okay, we just know that it is local max and local min there. We don't have to say write local min or local max. Right, but this case, as for the where is increasing or decreasing, we should answer that part first. So where is the function increasing? Negative infinity to negative 2, going up, and then from 2 to infinity. Decreasing, negative 2 to 0, and then 0 to 2. And of course, there's the partition number here, so we're not writing from negative 2 to 2. So that's why we need all the partition numbers. Right, so increasing, negative infinity to negative 2, from 2 to infinity, and decreasing there. Right, we have the sign chart already. Here we can also say the maximum and the minimum. So the local max equal to something that will happen at x equal to negative 2. And the local mean will happen when x equal to 2. And then we go back to the values here. When x equal to negative 2, the values is negative 4. And when x equal to 2, the values is positive 4. Right, so we have the minimum, local minimum at 2 equal to 4. And at x equal to negative 2, we have the local max equal to negative 4. Right, so to recap, we need partition number to put on the sign chart. We need the critical values is where the function, where the partition number is in the domain. If we just find the interval, if we only need increasing or decreasing, we really don't care what happened at the critical values. We don't need the values. We just need partition number. But if we find a local max and local min, just go ahead and find the values, because later on we will need the values for the function. So that will come in handy later. And with that, we finish section 11.1. As always, thank you for watching and see you in another video in business calculus.